Hello. I'd like to thank the organizers of this fascinating program for the invitation to be here and have the opportunity to speak with Professor Nikku Madhusudhan, or Madhu as he prefers. Today's conversation, titled From Molecules to Stars, will take us on a journey from the molecular fingerprints of alien skies to the grand story of how planets and stars come to be. Madhu and his team's scientific inquiry have transformed how we understand exoplanet atmospheres, uncovering the molecular recipes of these distant planets and how they form, giving rise to considerations of how they may or may not hold the ingredients to sustain life. These observations are not only momentous on their own, but as you will soon hear, are of potentially tremendous import for humanity as a whole, our place in the universe, and even our definition of life itself. So, Madhu, we're going to start with some of your observations. Your work has revealed astonishing details about the atmospheres of exoplanets. It represents something of a paradigm shift. For many years, exoplanet science was mainly about finding planets, counting them, tracing their orbits, and your work has helped to move us into the next frontier, actually understanding these. I believe that you have a few slides that will take us through some of your research.
Hello, everyone. Very good morning. Are you all excited? Yes? So, what is our future? And I mean it in the broadest sense, not us as a society, not us as a civilization, but us as a species. Right? Think about that. What is our future as a species? So for thousands of years, we as a species have always asked this fundamental question, are we alone? Are we alone in the universe, that is? Right? And our concept of when we talk about our place in the universe has evolved over thousands of years, all the way from not knowing absolutely anything about the cosmos to about 500 years ago, where we start to formally establish that the sun is at the center of the solar system, which is a trivial conclusion by today's standards, but it was as recent as 500 years ago when we were still questioning that. And did you know that we didn't know what the stars were made of until about 100 years ago? Okay? So even today, when we are thinking about are we alone in the universe, our concept of life elsewhere is mostly about life like us, like what is found on Earth, on an Earth twin, on an Earth-like planet. So that is the holy grail, if you will, is to ultimately find life on a planet exactly like Earth around a sun-like star, which is an Earth twin. But you want to ask the question, are we there yet? Can we actually do that? Can we actually find extraterrestrial life on an Earth twin? If you ask that question, there are two requirements. First, you need to find an Earth twin, right? Obvious, you need to find a planet around a sun-like star. The second is, if you found one, do we have the capability, the observational capability, the telescopes, to actually detect life on such a planet? The answer to both these questions is a big no. So sorry for disappointing you right at the beginning, but I promise the talk will end on a much more hopeful note, right? So what happened in the last 2 decades is we are going through a transformation in our understanding of planetary science and life in the universe, okay? Just in the last few decades. What we have learned is that actually Earth-like planets are not necessarily the most common habitable environments out there, at least we haven't found them so far, but there is a large range of other planets. So this is called the sub-Neptune regime. If you look at the solar system, there are the terrestrial planets, which is Earth-sized planets and smaller. And then there is Neptune, Uranus, and larger planets. These are gas giant planets with hydrogen-rich, thick hydrogen-rich environments, atmospheres. But then, if you look at planets around other stars, today, just in the last few decades, we have discovered over 6,000 exoplanets. And most of those planets are in what is called as the sub-Neptune regime, between Earth and Neptune in size, for which we have no analog in the solar system. Can you believe that? We have found thousands of planets, and most of them have no analogs, no similarities in the solar system. So the breakthroughs that are happening at the cutting edge of exoplanetary science are motivated by this very simple question: are any of these planets that are in between Earth and Neptune in size potentially habitable? Can any of these planets host life? So 5 years ago, we made a theoretical breakthrough in answering that question, and came up with this concept of Haitian worlds, which you may have heard in the news and elsewhere. These are planets with ocean-covered surfaces, no land mass at all, just completely covered in oceans, and thin hydrogen-rich atmospheres. The temperatures and pressures at the bottom of those atmospheres are such that they would allow for liquid water on the surface. Now imagine a planet like this that is habitable. So we have theoretically established this over 5 years ago, that these oceans could in principle be habitable. This is an artist's rendition, so it's not a real planet, just so we are sure. But then the star is a red dwarf star, like an M dwarf star. So these are the kinds of environments which we think are the best places to look for life today, because the planets can be large, much bigger, 2.5 times bigger than Earth, around 10, up to 10 times larger in mass than the Earth, and still be habitable. The planets being bigger means they're more amenable to observations, to atmospheric observations. Fair enough, so this was a theoretical prediction, but what about observations? So just 2 years ago, we looked at this planet, K218b, with the James Webb Space Telescope, and we wanted to see if there are any signs of atmospheric signatures in this planet. And this is using what is known as transit spectroscopy. Basically, when the planet goes in front of the star, you can measure the absorption of starlight that is passing through the atmosphere of the planet before reaching the observer, reaching the telescope. That's a cartoon of the James Webb Space Telescope. And these are some example observations where people have measured molecular abundances of other planets, like giant Jupiter-sized planets. So we then went ahead and said, can we actually look at this planet K218b with the James Webb Space Telescope? To give you a reference, this is a spectrum obtained with the Hubble Space Telescope. So you can see that little blip, and that was used to say that there is potentially water or methane in the atmosphere. But with just 14 hours of JWST time, what we found was this spectrum. This is amazing. You see these data points with error bars, and then the solid curves are models. That was a huge leap with just 14 hours of observation time with the James Webb Space Telescope. A subtle detail here is that this was the first time humanity has ever measured carbon-bearing molecules in the atmosphere of a habitable zone exoplanet. That happened just 2 years ago. Not only the carbon-based molecules, not only methane and carbon dioxide, but we also saw a tentative hint for a molecule called dimethyl sulfide in the atmosphere of this planet. It was a very tentative hint, but then we said, can we find this molecule elsewhere with another observation? The reason for that is that this molecule is known to be a biomarker. It's produced predominantly by life here on Earth. So then we went ahead and said, what would you predict if you looked at in the mid-infrared? And we found these are all theoretical models that you're seeing. We said that there could be those peaks in the spectrum if we looked at in a different wavelength range, and we actually found it. Isn't that crazy? This is just from this year. Early this year in April, you may have heard in the news of the first hints of life elsewhere. This is what we are talking about. So these are still tentative hints. We are talking about 95% to 99% confidence and the molecule being there against a model with the molecule not being there. But that's not good enough for science. We want to be sure at a level of more than like 1 part per million confidence that the molecule is not there. You see what I mean? We need to be sure that the molecule is definitely there at a very high confidence. So this is not good enough for scientific discovery, but it's good enough for us to be motivated to look further. So these are the first tentative evidence for the presence of potential biosignatures in an exoplanet. So these are obtained with two different instruments, so independent evidence. And as with every major discovery, there's a lot of debate going on in the field about how to interpret these observations. Are we actually seeing the biosignature or not? But so I put in all these questions up front just for completeness. So there is a lot of debate going on. But you can also ask, is K218b unique? And the answer is no. This is another planet, QI270d. And this paper from this whole data set is out today, actually, on the archive. And we are also finding similar signatures of complex molecules beyond just methane and carbon dioxide in the atmosphere. So I'll summarize this by saying there are three fundamental advancements that have already happened with these initial observations. What we may be seeing is the first contact with a potentially habitable environment or more than one, which is wild because this is the first time in thousands of years of our history in looking for life, finally we have data that we can see tentative signatures in and that we can debate about. And then this is a unique congruence of theory and observation, as you know, is fundamental to sciences, where we made the theoretical prediction before the observations, and the observations go ahead and confirm it. And then regardless of whether these particular planets are habitable or not, we are seeing a new class of temperate sub-Neptunes that are potential for observations. So this decade, with these new facilities and these targets, are serving as, would serve as the launch pad in the search for life. So in my mind, the question is not whether we will find life. There is a good chance we will. The question is, are we prepared to find life as we don't know it? Think about that.
Okay, so thank you for that. That brings up quite a few questions that I'm sure you'd all like to hear the answers for. So if we think about what you said in your reference to Copernicus and the sun-centered solar system, we know that over time, science's wisdom brought us to the truth. And again, we have a lot of deeply ingrained biases and preconceptions towards what you're talking about today. What is, in view of what you've seen and what you've discovered and what you think you'll find ahead, what is in the broader context, the historical context for understanding not only our place in the universe, but also the philosophical implications of how we will look at ourselves going forward?
Yeah, so this is a momentous occasion, like in the history of science that we are going through. We are witnessing history as we speak. So as you rightly pointed out, so just to establish that the sun is at the solar system and the earth is going around it, people had to sacrifice a lot, sometimes even lives, in trying to convince everyone that that is the case. And it took us hundreds of years to get here. So finally, we have the data to ask the question, are we actually alone as a species, as life, right? So obviously, there will be a lot of debate around it, and we are going through those debates right now. But I think we are much better equipped right now to handle debates and arguments for and against this. And the implication on society is deep, is that for once, we will transport ourselves from being confined to a planet, psychologically, to this planet, to being a cosmic species. And to me, that is the biggest difference, is that you walk into the night sky, like you walk outside, look at the night sky today, and what you're looking out there is an inanimate sky with physical objects, the planets, stars, galaxies, and all that. That's what you're seeing. Imagine a future, not a very distant future, maybe in this decade itself, in the next few years, or maybe in a few decades. Imagine walking out, looking at the sky, and knowing that there's a planet out there, there's a star out there, which you can see, with a planet around it, which is known to have life or signatures of life. What you're looking then is not an inanimate sky, but a living sky. It's like looking at a beach or a garden. And that is wild if you think about it, right? So that is our future. So our identity as a species is not that we are inhabitants of Earth, but that we are actually a cosmic species where the Earth is part of that cosmos. And I think that has huge societal ramifications.
It's huge indeed. But as you conduct your research, what you're doing also is you're challenging all of our assumptions about what planets and life could be. You're looking at worlds rich in carbon, oceans of exotic materials, even atmospheres completely unlike our own solar system. So this broadens our very definition of what life might be, habitability, and it reminds us that life can arise perhaps under conditions very different than the Earth's. So what are some of the most interesting things that you've seen about exoplanet compositions, and how close do you think we are in determining life, whether it's life as we know it or another form of life?
Yeah, so thanks for that question. One of the biggest assumptions we have made all along, even within the sciences, is that we have to look for life like Earth on an Earth-like planet. This is what I was hinting at in my talk. So with these theoretical and observational breakthroughs happening simultaneously, what we are realizing is that actually the environments could be extremely different. We are talking about planets with just entire oceans, no land mass, and the oceans can be very deep. On Earth, they're of the order, like you can go up to 10 kilometers or so for the deepest oceans. Whereas on these kinds of planets, the oceans can be hundreds of kilometers deep, and there is no ocean floor, there is no sand floor in the ocean. The water would transform into high-pressure ice at the bottom, right? So just to imagine what those environments would be like is already wild. We don't have any concept of such planets. So we are having to do the theoretical calculations, be imaginative about it, and do the observations simultaneously. So this is a diverse set of environments we are thinking about. And the atmospheres are hydrogen rich. They're not nitrogen or oxygen rich like we see on Earth. They're hydrogen rich. That has some benefits for life, but that may also have some counter benefits or disadvantages for life. And we are trying to work all these things out as we speak. So we are seeing a vast diversity. I mean, theory is one thing. We can do all the theory, but ultimately you need observations to confirm them. And the greatest thing now is that we actually have those observations. We are already seeing these molecules, methane and carbon dioxide for sure, but also these other more complex molecules that are potentially indicative of life, or some other complex chemical process that we don't know of. So we need to remain open to all those possibilities and tread carefully as we go ahead. So we don't want to claim that we have found life prematurely. We only have candidates, but we want to do our due diligence before we get to that point.
Okay. So this brings us, your observations, and you're looking at life perhaps in a different context to what we're used to, can possibly help us in understanding the origin of life here on Earth and potentially elsewhere as well. And this is one of the largest unsolved queries of science. For centuries, we've asked if the Earth could be the exception, just an accidental mixture at the right moment and time of it, or could it be a chemical inevitability that may occur elsewhere? And this is something that for centuries has not been able to be solved. If you think about the renowned scientist Francis Crick, he believed that original living cells traveled through space on an asteroid and landed to be a starter colony of life. And interestingly, all 20 amino acids, if not actual living organisms, have been found in space. Now, you know also that there are many origin of life studies here that look at RNA scenarios, spontaneous emergence of Darwinian evolution in physical chemical systems. So what are your thoughts on how this can help us in understanding how life started?
So I want to make two very important points here. One is that if you think of all the laws of physics and chemistry, right, that you read in textbooks, what we also know is that these laws don't just apply on Earth, but they apply universally. So we can look at stars, planets, galaxies, and all that, and we know that many of the physical principles that we talk about here on Earth also apply on a cosmic scale. But there is one area, a fundamental area of human exploration that has never been tested cosmically, that's biology. Because there is only one example we know, that's the Earth. So a detection of life automatically, even one detection, automatically makes biology a universal process. Mm-hmm. And that's a huge jump in our understanding of fundamental processes. So from a scientific point of view, that is one major breakthrough that will happen. The second bit, and more directly to the origin of life, is that here on Earth, as you pointed out, we don't know how life originated here on Earth, which may come as a surprise for many of you, but that's a big open question even on Earth. So what we think will happen is that by looking at these very diverse environments that are nothing like Earth, if we find life there, so those sorts of observations will inform us on the diversity of conditions under which life can emerge in planetary systems. And that could instead, in turn, help us understanding how life originated here on Earth. So can you imagine trying to solve one of the biggest fundamental questions on Earth by looking at a planet that is hundreds of trillions of miles away? Right? This planet, K218b especially, is 124 light years away. That's hundreds of trillions of miles. So that's what we are talking about. It's wild in all sense of the word, is that you're looking at planets that are trillions of miles away and making atmospheric observations. You can establish the conditions as well as the potential presence of life on them. And those sorts of observations will help us inform us about biological processes here on Earth and how they emerge. So I think that we are going through a very wild time in the scientific exploration of our own planet as well.
So our oldest concept of life has been the one that has served us best until recently, that the notion that all life derives from previous life. This doesn't exclude new life evolving from earlier life, but it does exclude things that do not arise from previous life. Robotic life, artificial life, digital life, etc., are by this definition at least not life forms, unless they come from something that's already living. Almost everything that defines life can be synthesized, but the complexity of putting everything together exceeds that possibility for now. So I just have come from a program at NYU where we looked at how DNA structures are being used from everything from therapeutic tools to robotics and a range of other applications. And this further blurs our current definition of life. So are we prepared to redefine life as we know it?
That's a very good question. So in summary, are we prepared to identify life as we don't know it, and are we prepared to redefine life as we know it? And I mean, we don't have a good answer to that question right now. We are at that very edge of scientific discovery where there are more open questions than there are answers. But what we are fortunate is that we are even sitting here and talking about it, where we have actual data. Right? So our starting point right now is to use the Earth as a template and the life on Earth as a template to begin with. So for example, if someone asks, well, if you found DMS in K218b or other exoplanets, what does it mean? What kind of life are we talking about? So we don't know yet, but what we do know is that life on Earth, most microorganisms like phytoplankton produce DMS. DMS is mostly produced by marine microorganisms. And such organisms were there very early on in life's evolutionary history. So that is our baseline assumption, is that we are looking at least very simple microorganisms that could be producing these molecules. But how much more complex it can get, there is no upper limit, right? So don't imagine every sort of complex life you can. Let's stick to the basics and say at least there is microbial life, and then work from there as we gain more and more data in our inferences. So we have to be scientifically robust about it. But you're right that we don't have a good definition for life even on our own planet. And welcome to the frontier of science, is that there are burning open questions like that, and the show must go on. We must make more observations and see if we can piece together a unified picture.
Well, I think also what you're saying is that this could be replaced, life could be replaced by a new definition, perhaps with several nuances.
Absolutely, absolutely. What excites me most is that the diversity of environments that we are seeing, and just imagining the kind of life at any level of complexity that is possible. So we need all those theoretical and experimental work. And then we also need the observations to find these molecules and see if there are any non-biological explanations to them. And if not, then life ends up becoming the most favored explanation. and then we have to work backwards to see like what sort of life is possible if we start from like the very basic principles of life on Earth. But as you said, like there are a lot of open questions on how we define these things, even in biology. So we have to keep an open mind and we could be wrong in many ways, but at least the journey has started, right? And that to me is wild, that the journey in our search for life has started where we are beginning to get data. And looking forward, in the future, we'll look back on this moment, and I'm pretty sure we'll be saying 2023, 2025 is when that like transformation happened, when we finally as a species started to get enough data to actually ask the question, is this life that we're looking at?
Well, I want to put Madhu's work into context in a way. Any discovery of life beyond Earth would be one of the biggest discoveries in human history. Just even this discovery of simple life would answer the question whether life is a rare accident or a natural outcome of the universe. The discovery of intelligent life would have major implications, and as Carl Sagan once said, it would be a humbling reminder that we are not the center of the universe. And we can thank this man and his team for bringing us to this point where we're even asking that question. I think that this is a topic that is going to continue to evolve, perhaps even quickly. And we look forward to continuing the discussion. So I want to thank you. And if you have anything else you want to add, please do.
Thank you, Lorie. I would like to thank the organizers and everyone here for making this session happen. But I would also like all of us to congratulate ourselves as a species, right? To me, it's really wild. I live through this day and night in trying to make these observations, build these theories. But if I take a step back, it is a celebration of us as a species that over thousands of years of modern evolution and tens of thousands of biological evolution and millions of years of more complex evolution, that we have finally arrived at a stage where we are a technologically capable cosmic entity, right? We are no longer a unique species sat on one planet and the rest of the universe being inanimate. We are actually a cosmic entity. We have the capability to look and say that if that planet's got life on it, we will be able to find it. So to me, it's no longer about national boundaries, about geographical boundaries, and there are big questions on Earth that we have to solve, but also us as a species as a whole. I think we can congratulate ourselves in arriving where we are at after thousands of years of modern scientific evolution. So thank you, everyone.